Welcome to lesson 2.2. So we're going to be adding vectors pictorially. So we were introduced to vectors. What are you doing? Introduced to vectors last time. Remember, a vector, usually you represent it with an arrow, but it has both a magnitude, which is kind of like how long it is, which is kind of like how strong is it. Is it 50 pounds of force? Is it 100 pounds of force? That would be an arrow twice as long. Or is it a speed, 50 miles an hour? Is it 100 miles an hour? It would be twice as long, and so on. But the magnitude you can measure like with a ruler, and then you have to say its direction. Which way is it pointing? That's like a theta. Which way is it pointing? That's part of those two things together, a magnitude and a direction. Push this hard in this direction, or move this fast in this direction, or something like that. That's what makes up a vector. So we're going to start adding two vectors together. Last time we basically said, oh, here's the rectangular form, and oh, here's the polar form, and it's good to know those, and we'll use both of those today. But today I want to add two vectors together. And we're going to do it not by crunching numbers so much. We're going to do it pictorially, by drawing them. We're going to draw them. We're going to measure them and draw them and see what we get. So this is a really good way to start playing with vectors. So anyway, we'll need of course we'll need a ruler to measure the magnitude, and we're going to need a protractor to measure the direction. And before we get started with actually adding any vectors, I wanted to kind of go over how do you use a protractor, because a lot of people are a bit rusty on this. So let's explain how you use a protractor. So of course that is a protractor right there, right? That semicircular thing. And you'll notice a couple of features. First of all, usually when you're using a protractor, you have sort of an XY axis or something equivalent in mind. In this case, it's a north, south, and east, west axes, but you have some kind of coordinate axes in mind. And notice how I've lined up the protractor. Maybe I should erase that now. You get the idea, right? Okay. You've got some kind of XY axes, and then what you're trying to do is you're trying to, see that line there? You're trying to line that up with the positive x-axis, and then you see this line here? Trying to line that up with the negative x-axis, and you can see these lines, or this line anyway, well, this line, the 90 degree, put it that way. These lines should be lining up on your y-axis almost perfectly, as good as you can get it, right? And actually, you might also notice there's a bit of a crosshair right there. But I don't really want to cross out. Okay, there's a bit of a crosshair right there, and if you're lucky, it's got a little circle in it, and so boy, it looks like I kind of didn't place this one right. But ideally, you want that little circle to be like right on where the crosshairs come together, right? Lines up pretty good over here, lines up pretty good over here, so I'm not exactly sure what happened there, but whatever. You try to line up your protractor as best you can, and it's never going to be perfect, but you do try to line it up as best you can. So again, what are you doing? Get these lines. This represents like 0 degrees, you might say. This might represent 180 degrees. Get those lines lined up nice. There should be like a crosshair here, but the 90 degrees too. Get those lined up on the north-south. And when they're lined up, you're ready to start measuring. They're lined up. What do you say we start measuring? Okay. First question. What angle is this line at? Now, before you answer, I should always specify what form I want. There's at least two ways that you can form your angles. One way to form your angles is called standard position. So if I ask you, what's that angle, this one here, what angle is that line making in standard position? Standard position means measured counterclockwise, which is this way, from, you might say, the east or the positive x-axis. In other words, this is 0 degrees. Due east or positive x-axis is 0 degrees. Always, always, always. In a math context, if you're talking angles in standard position, 0 degrees is to the east. Always, always, always. So try to keep that in mind, that it's always positive x-axis or due east. And then if that's 0, and if you're supposed to rotate counterclockwise, then what you'll be doing is you'll be reading off and going this way and saying, how many degrees did I just move? And the 70 right here is kind of telling you that, right? So that would be 70 degrees. And just to emphasize it, I'm going to put an SP that's actually readable. I'm going to put an SP there just to emphasize that is 70 degrees in standard position. Okay, if that's 70 degrees, what the heck is 110 all about? Well, you might notice that they're measuring kind of counting this way. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110. They're counting this way, which I guess some people might want to do, but not us. Not when we're measuring standard position. So again, you got to be suspicious about the way they've labeled the protractor, okay? Often I almost ignore those numbers. Don't make it a point to make those numbers always work for you. Just say, look, I got to go 70 degrees, and I know this is 0, and I know I got to go counterclockwise. And I look at these, I go, well, every tick mark's 10 degrees. So it's 10, 20, 30, 40, 50, 60, 70. Yep, I went 70 degrees counterclockwise. My angle is 70 degrees in standard position. So I hope you're grooving on that pretty good. What about this one? What's the angle in standard position? Well, maybe I have to get a different color, huh? In standard position, again, this is always the case. Standard position is measured counterclockwise from east, or in other words, the positive x-axis. This is 0 degrees. I don't care where you're going to end up. You're going to start there, due east or the positive x-axis. And then you're going to rotate counterclockwise. So I go like this. I go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130. So this would be 130 degrees in standard position. So in this case, yeah, it looks like the 130 is the one to look at. Don't look at the 50. The 50 is measuring from west. We don't want west. We want east. Okay, so fine. Okay, so over here, just 2 more, just for fun and giggles and stuff. What angle does that one make? That's not supposed to be 0. That's supposed to be a circle. What angle does that line make? This one here. Well, again, 0 degrees is due east. So I'm measuring, well, you're supposed to measure counterclockwise, right? That's what this is saying. Now, if you can go clockwise if you want, but just pretend it's the negative direction, because actually that's what it is. So it'd be 10, 20, 30. This would be a negative 30 degrees in standard position. Okay. You could also, if you want, rotate all the way around this way. Now remember, if you turn around, that's 180 already, and then you keep adding 180 until you get all the way over to here. It's going to be a lot. 180, 190, 200, 10, 20, 30, 40, 50, 60, 70, 80, 90, 300, 10, 23. That would be the same as a positive 330 degrees. Same thing, same thing. But usually negative 30 is a little easier to think about, I think. So anyway, that's that one. And then my final question for this set is, well, what angle is this line at? Standard position. Remember, when you say which direction, you should really specify what kind of direction do you want. I want a standard position angle. Okay, well, what direction is that? So back to my other color. So again, 0 degrees is over here. You have to start over there. And if you're a good boy, you will go counterclockwise. And once you get over to the west, that's 180 degrees already, right? When you turn all the way around, that's 180 degrees. And then I'm going to count basically these little bitty marks. You know, each one of these is a degree. So you'll notice if you kind of stare at this long enough that you go 15 degrees. So that's another 15 degrees. So it's 180 plus another 15 is a 195 degree angle in standard position. 195 is usually how I would say that. Now, if you want to rotate in the negative direction, that's kind of like fine. And you'll end up with, I invite you to try it yourself, you'll end up with negative 165. Usually, negative angles are fine if you're going to be in the 4th quadrant somewhere so that you don't have such a big negative number. But if you always give a positive number, that's going to be fine too. Between 0 and 360 preferably. But that's standard position. Okay, fine. There's one other way. Bearings. Sometimes headings. I'm pretty sure those are synonymous. A bearing or a heading. What am I talking about? I'm talking about this. So are these the same angles? Same angles. Okay, but we're going to be expressing them differently. So this is a bearing of what? Well, the way bearings work, there's a different always. So up here, you always start at 0 degrees and you always rotate counterclockwise. Okay. With bearings, you always start either north or south. You either start from the north or the south. You never start from the east. You never start from the west. This is a different way of stating your angles, your bearing, your heading, whatever you want to call it. Always start either north or south. So if I want this angle here, and I want to start from the north, well, how many degrees did I go to get from there to there? Is it 70? Is it 110? It's not either one of those. So again, don't let the numbers on the protractor throw you. Keep in mind what you're doing. I'm starting at north and I'm measuring how far am I going from the north. Well, I'm going, that would be 20 degrees. Now, since it's 20 degrees, and it's not 20 degrees this way, it's 20 degrees this way. You gotta be able to distinguish those two, right? So we say it's 20 degrees towards the east. North, 20 degrees east. That would be the bearing. So the way bearings work, you start either north or south, and then you rotate your angle by this much towards this direction. So I started north and I moved 20 degrees towards the east. That's what that is. You got to guess at how we would represent this angle as a bearing. Well, you would start either north or south, and here north is a lot closer than south, so I'm going to start at the north and I'm going to go towards it. Starting at the north, I have to move how many degrees? It's like I'm spinning my head, right? Now, again, these numbers are going to throw you, so don't worry about the numbers. Count the tick marks. 10, 20, 30, looks like an even 40 degrees. Cool. So this would be north 40 degrees towards the west. That would be north 40 west, okay? You get used to these pretty quick, I think. You just got to make sure you understand. You always start either north or south. You never say east 70, north, or you never do anything like that. It's always starting north or south. Civil engineers will like starting north. Do you guys like starting south? I don't even know. I know they like starting north. I know they hate starting east, but whatever. So let's look at these two. How would you, maybe you could take a guess at these right now. Let's look at this one first. Which is closer, north or south? South is closer. So we're going to say south. And then the question is, how far do I have to rotate from due south? I have to go 10, 20, 30, 40, 50, 60, it looks like. So south, 60 degrees to the east. That's that bearing. So again, the 60's got nothing to do with the numbers you're seeing here. Don't let that throw you. This one, you got it? This one, it's very tempting, I think, to start from the west and come down, but no, that's not what the rule is. The rule is start either north or south. Well, I'm closer to south than north, so it's going to be south, and then I'm going to have to rotate this far to get there. And if you just count by tick marks and stuff, so 10, 20, 30, 40, 50, 60, 75. So south 75, and you could put the degrees if you want. South 75 degrees to the west. That's what that bearing is. So take a look at these. I've pretty much covered every quadrant, right? So either you're in the first or the second, just the first quadrant, or it could be in the second quadrant, you could be in the, this would be the third quadrant, this would be the fourth quadrant, right? So every quadrant's covered here. You're either measuring from north or south, just keep that in mind. Okay, so now we get to the main show. We're going to start adding vectors together. This is practical stuff right here. So let me switch back to blue. Adding vectors tip to tail. So here's our little problem. We've got a personal aviation device. Those sound like fun, don't they? And this one's flying 55 miles an hour. Okay. And it's at a bearing of north 70 east. So you just got an idea what that is. There's north, there's east. So face the north, you might say, or start from the north and then measure 70 towards the east. It's like way over there. It's going that way somehow. Anyway, just to get an idea what's going on here. So the personal aviation device is going that way, but it's in a crosswind, and the crosswind is 40 miles an hour. That's going to carry the device a little off course, don't you think? It's going 55 and the crosswind is 40. Yeah, that's going to have an effect. And the crosswind is blowing in a different direction, so it's really going to have an effect. It's north 15 west, which would be, here's north, rotate 15. It's going this way. So the wind is going this way. The personal aviation device is going this way. So which way is he really going? If you look up in the sky, which way is he really going? Well, he's going to be pointing this way, but he's going to be, because of the wind, he's going to be drifting, right? He's going to be drifting with the wind. So in order to solve this problem, we can actually add these two vectors together. And the first method I want to look at is tip to tail. So that means you draw one vector, pause, and then draw the other vector. You draw this vector starting at where you ended the other vector. Get it? That's the tip of this vector, and that would be the tail of the next vector. Tip to tail, that's what we mean. So I already kind of did that, but let me explain how I did that. So first thing you got to do, get maybe a different color out. 55 miles an hour, that's going to be measured with a ruler. North 70 east is going to be measured with a protractor. So you got to pick a place to start. So I actually started way down here. This is my starting point. That is my starting point. And it's easier to measure the direction first. So what was the direction? I sure hope I got this right. North 70 east. North 70 east. Well, that's north. And if you rotate 70 towards the east, you get to this direction. So this would be north 70 east over here. So that's the direction. And usually what you'd do is you'd make like a little tick mark on your, you'd make a little tick mark on your protractor. Then you'd get out your ruler and just pretend I have a ruler here. I get out a big ruler, let's say. You get out your ruler and you want this vector to have a length of 55 miles an hour. So you have to choose some kind of scale on your ruler. I don't know if you want to use 1 inch equals 1 mile an hour unless you want to draw a 55-inch vector, but I don't. But you choose some kind of scale. Centimeters often come in handy. And I don't even remember what the scale was that I drew. Maybe I could figure it out. That's a 55, huh? Well, you know what? I do it on the computer, which means all bets are off. Anyway, this is like so many centimeters is so many miles an hour. The point is use your ruler so that, come on you, come on you, come on you. Okay, use your ruler so that the length scales to 55 somethings. Could be millimeters, could be centimeters, could be inches, could be quarter inches, could be half inches, could be eighth of an inches, whatever it is. 55 somethings. The length of that should be 55 somethings measured on your ruler. And again, it's going this way. So once you've got the direction figured out and you've got the length figured out, you can finish drawing your arrow. And you say, there I am. That's the first vector. What is that? That's 55 miles an hour at a direction of whatever the heck that was. North 70 east, I guess. That's the first vector. I drew it. Cool. Now we're adding 2 vectors, which means now we've got to draw the other vector. Where's the other vector? It's right here. It's 40 mile an hour wind blowing in this direction. Tip to tail means I come up here to the end of the vector that I just drew, and this is going to be my new starting point to draw the next vector. So notice I've got these crosshairs just for reference. Try to keep your north south. These things are great if you happen to have a T-square. If you have a T-square where you can just kind of slide the T-square up and down on the board, you can always keep your horizontal lines the same, but you just kind of have to eyeball it for the purposes of this homework, or get out some graph paper. Graph paper gives you a pretty good guide for what's horizontal and stuff. But anyway, that's our new crosshair. So starting there, we want to draw the next vector, and the next vector was, I do the direction first, north 15 west. So you get out your protractor, stick it down there so that the crosshairs are on this blue dot, and this lines up, and this lines up with the due east-west direction, and then this lines up with the due north direction, and then you've got your protractor placed pretty well. Then you have to mark off this angle of north 15 west. Now that's the north, and then you'll see that I counted 10, 15. I rotated 15 towards the west. Make a little tick mark. Now if you want, you can draw like a guideline, draw like a light guideline in light pencil or something and say, well, the vector goes along that direction there. But then you got to get the length correct. So you get out your ruler. I need the length to be 40 somethings. So this was 55 somethings. Now of course you want to use the same kind of somethings. This was 55 somethings. This has to have a length of 40 somethings. So I'll say measure length of 40, and I won't say somethings, I'll say same things. So I'm not sure if these were quarter inches or what I used, but I had 55 of them down here. From here to here was 55 of them, and from here to here was 40 of them. Okay, cool. So there we are. We joined the 2 vectors together. Start tip to tail, start to finish. Now we started down here. In fact, I'm going to put that in red, come to think of it. By golly. So give me red. This was the starting point down here. and this is our ending point up here. Now adding those two vectors together means go back to your starting point over here, put your ruler down, come up to your ending point over here, put your ruler down, and my ruler doesn't seem to be long enough, darn it. Oh, let's see if I can get another ruler real quick. Oh, my kingdom for a ruler. Where'd it go? Here it is. Okay. I got me a nice ruler. So I'm going to put my ruler down. You can't see this, of course, because it's kind of off the screen. But and I'm going to try to join these as best I can. Boy, this is kind of hard. Come on, you're a pencil. You're supposed to draw. You're supposed to draw. It won't let me draw along the ruler. It must be some kind of it's a metal ruler, so it must be some kind of magnetic effect or something. Anyway, pretend I drew that with a ruler. This is your answer. By the way, this is sometimes called a resultant. So if you hear me use that word, that's all it really means, is when you add the two vectors together and get a result. Don't just call it a result. Call it a resultant. Yep. So anyway, those two this is the way the guy's really going to move. So if you're looking down from a stationary drone or whatever, right, you see the guy aiming this way. This is the way he thinks he's going. But the wind is making him drift. So he's always pointing this way. He's pointing this way all the time, but he's drifting. And then this red arrow that we drew by joining our beginning point to our end point, that is which way he's really moving. And if you want to know which way is he really moving, you can get out your ruler and you can measure the length. And I wonder if I could do that. So 40. Oh boy. I've got a scale of. Okay, I think I can do this. So this is something like 10. Come on, you get out of the way. I have a ruler on here that I'm trying to measure the length of that red arrow. And it's something like 70, I don't know, 73 or something. You might get a slightly different answer. But it's something like 73. And is that believable? Well, if you went 55 this way and 40 this way, well, it's got to be something bigger than 55. It's got to be bigger than 40. And it can't be as big as 55 plus 40 is 95. It can't be that big. Because if it was that big, these would have to be all straightened out, right? So, yeah, 73 sounds about right. And then which direction is it going? Well, you just look at your protractor. I still got the protractor here. This angle in standard position would be, it looks like, pretty darn close to 60 degrees, doesn't it? So something like 73 miles per hour at 60 degrees, or actually polar form. We usually use this kind of a notation. So that's about what I'm getting. Wow, that's pretty cool. Or actually, 60 degrees would be the same as north, 30 east. I invite you to verify that real quick. So anyway, this is our general method for adding vectors tip to tail. Draw one vector, and when you get to the end of that vector, start there, draw your next vector. Go all the way back to where you started, go all the way to where you ended, join those 2 points. That's how you find your answer, your resultant, or what the adding up the 2 vectors gets you. Oh, I got a soliloquy here. One of my favorite words. Soliloquy. You face the audience and you share your thoughts. Soliloquy. This is tip to tail. There's another method you'll see if you go Googling, and it's called parallelogram method. And I can get you the parallelogram method by saying this. Tip to tail. It doesn't matter which one you draw first. It no matter. It doesn't matter which one you draw first. This will actually get us at the parallelogram method. Trust me. So let's just say I had drawn, this one first. Well, it would be somewhere up around, this way-ish. Well, I should really use a pen. It's going to be up somewhere around this way-ish, and it's going to be about, trying to get the length about right. Just estimate something like that. And then draw this vector, which is going to be going that way. And guess what? You're going to end at the same spot. Give me a pen. You're going to end at the same spot, especially if I drew this with a real carefully, these would look more like this, I guess. There we go. And So that's one thing, tip to tail, it doesn't matter which way you go. But the other thing is, if you look at this overall shape here, it's not quite a rectangle. It might look close, but it's a little crooked, right? It's leaning over a little bit. That shape there is technically a parallelogram. And all a parallelogram means is that the opposite sides are parallel. A rectangle is a great example of a parallelogram, but you don't have to have 90 degrees is what I'm saying. It doesn't have to be 90 degrees to be, you could make it really, really crooked. There's a nice parallelogram, something like that. So that's the parallelogram rule. So the parallelogram rule says if you want to add the vectors, you could draw one vector and the other vector both starting at the same spot. Instead of tip to tail, just draw them both starting at the same spot, and then use those two to define the sides of a parallelogram, and then go right across the diagonal of the parallelogram, and that's going to be the same answer. Okay, so parallelogram rule, that's kind of a nice rule, I guess. Tip to tail is really practical if you're actually using ruler and protractor. Cool. So I think you get the idea. We're going to draw the vectors and join them. Now I'm going to do that here. You're going to have to trust me that I've got a protractor right here in front of me. So I'm going to call that start. Take one vector. It actually doesn't matter which one. I want a 20-degree angle. So if I got my protractor on here, that would be 0. That would be 20 degrees. And I want to have a length of 3. Okay, fine. Length of 3. I think we want to use something else. I'm going to try to measure a length of 3 going in that direction. I'll stick to my protractor. It's easier. It's got a ruler on the end of it. So I'm going to draw these kind of small. So be right about here. So that would be a length of 3 at an angle of 20 degrees. Now, starting at the end of that one, draw that. So first of all, it's at 57 degrees. So I have to put my protractor back on here. And of course, if you move the protractor, it moves the whole darn screen. But you put your protractor on there, try to keep the very same horizontal and vertical, X and Y directions or whatever. And 57 degrees would be just about here. I'm making a tick mark. And if I wanted to go a distance of 5 in that direction, that would bring me to just about, wow, almost to the top of the screen, right there. So I kind of go, okay, there's the next one. So that would be the 5 at an angle of 57 degrees. Okay. And now to get the answer, what do you get when you add those two together? Well, you started here. You ended here. So you join where you started to where you ended, preferably with a nice ruler. You can now measure both the length and the direction of the red arrow. Now the length of that red arrow, what did I get? How did I do this? Okay, so I've got something like, this is going to be a little off, of course, but I've got something like 7.5. Does that make sense? Well, it's got to be bigger than the 5, and it's got to be bigger than the 3, and it can't be quite as big as 8, right? Because there's an angle here. These aren't lined up, so it's not going to be quite 8. 7.5 is actually a little surprising, but 7.5, and then the angle, I get my protractor out and I measure it. Again, I'm measuring it from here. Notice these angles are standard position, so I feel I do not feel any obligation to use anything else, put it that way. And I lost my protractor. Where'd you go? Come here, you. It's trying to get away from me. Okay, so that angle is just about, and your answer might vary a little bit because I'm using a very thick Apple pencil, but this is something like 44 degrees. So if you get something in the ballpark, consider it good. Okay, so again, that's our method. So notice this is polar form, polar form, polar form. Everything's polar form. Oh, by the way, we might note, if I just go back here for a little bit, did I add 3 and 5 to get 8? No. Did I add 20 and 57 to get 77? No. So it's not adding as in math class, it's adding as in vectorially, geometrically, or adding pictorially, whatever word you want to use. So when you add vectors together, you really got to scale it out and see what you got. Example 3. Here's 2 vectors. You might recognize these are not polar form anymore. what are these? These are rectangular form, which means that's an x-coordinate, v sub x. That's a y-coordinate, v sub y. But you're going to start the same, and you're going to kind of do the same thing. You're going to draw your two vectors. First, you draw one vector. Pick a starting point. I'm going to pick right there for my starting point. Now, the first vector has a length of 2.8191. So I'm going to say that's 0.2, 0.4, 0.6, 0.81, 0.2, 0.4, 0.6, 0.82, 0.4, 0.6, 0.8, 2.81, yeah, somewhere around here. So the first vector is something just about like that. It's going to be a little bit of approximate, of course. That's the first vector. Oh, wait a minute. No, it's not. I hope you see my mistake. That's not the first vector. All I drew was this part, the x component. Now I got to do the y component. Go up 1.02. So 0.2, 0.4, 0.6, 0.81. It's right about there. So start here, end there. The first vector looks just about like that. Now, next vector. This one, oh, let's use this weird color, has an x component of 2.7. Now, where am I measuring from? The end of my first vector. That's his tip to tail. 2.7, 2, 4, 6, 8. That's a 1. 1.2, 4, 6, 8. That's a 2. 4, 6, 2.2, 4, 6. This is 2.7 right about here. Right about there is 2.7. I don't actually want to draw that. No, I don't. That's how far I go in the x direction, and then in the y direction, whoa, I gotta go 4.2 almost, huh? 0.2, 0.4, 0.6, 0.82, 1, 2.4, 0.6, 0.82, 0.2, 0.4, 0.6, 0.83, 0.2, 0.4, 0.6, 0.84, 0.2, somewhere around there. That's my end. Connect the start to the end, and you got something like this. So those two vectors, when you add them up, what do you get? You get this. So this is the answer. This is the resultant, whatever you want to call it. When you add those two vectors together, you get that one. What is that one? Well, they gave us rectangular form. This is rectangular form. We could give them polar form, but we could also give them rectangular form. Why not give them rectangular form? So in rectangular form, see if you believe me. This was a 2.8191. And this was a 2.7232. All we really got to do is add those two numbers together, which I didn't do. So anyway, 2 and 1 is a 3. Yep. 3 and 9 is a 12. Carry the 1. So 2, 3, and a 1 is a 4. Cool. 7 and 8 is a 15. Carry 1, 2, 4, 5. 5.5423 in the x direction, and then in the y direction. This was a 1.0261, and this was a 4.1934. So we add those two numbers together, because we went this and this in the north direction. So 4 plus 1 is 5. That's a 3, right? Yep. 3 plus 6 is 9. Cool. That's a 9, right? Yep. 9 plus 2 is 11. And then 1 plus 0 plus carry the 1 is a 2. And then you get the 4 plus the 1 is a 5. Oh, wow. So it's almost 45 degrees because these are almost the same length. If x and y have the same length, it's at 45 degrees. But anyway, isn't that kind of cool, huh? So you can just add, see, now I want to get rid of all this stuff again. You can just add this plus this together to get my x component. So you add your two x components to get the total x component. And then you would add the two y components to get the total y component. And assuming I did the addition correctly, that would be your answer. So that's pretty cool. So there's something really nice about rectangular form. They're very easy to add. You just add the x's and the y separately. Contrast that with adding the with these. Again, you can't add the 3 and the 5 and get 8. No. You can't add the two angles. No. But with rectangular form, you can simply do that. Add the x's and add the y's separately. One more concept for this lecture here. It's something called static equilibrium. What's that? It basically means nothing's moving. So if you have a bridge and it's not falling down, that's good. And that's called static equilibrium. It's in a state of static equilibrium. Or if you have, in this case, picture there's like a ceiling up here somewhere, and these two cables are attached to the ceiling. There's a cable here, there's a cable here. And right there, there's, I don't know, an eye hook, just a knot, whatever. And you've got this weight hanging down here. Well, if it's not moving, it's in a case of static equilibrium. And if it's in a case of static equilibrium, as it says up here, in a state of rest, which means static equilibrium, all forces balance to zero. Why is that? Well, picture this hockey puck, right? If I'm pulling 10 pounds this way and 10 pounds this way, do you believe it won't move? I believe it won't move. It's like a tug of war where everybody's pulling at the same thing. Well, if you're pulling, hey, come back here, you hockey puck. Okay, so if it goes this way, you got a 20-pound force this way and there's nothing over here, it's going to move. It's kind of like you just whacked it with the hockey stick with a 20-pound force. Well, of course it's going to move, right? So if their forces are not in balance, if they're not canceling each other, if they're not adding to zero, it's going to move. So if it's not moving, that means they do cancel. They do balance. They do add to zero. They do. So that means we can figure out what this weight is. We can solve for this weight. Why? Because I know I got a 500-pound force at 60 degrees. Just kind of draw that. Right? Measure your 60 degrees out. And then tip to tail. Now draw a 289-pound force at a 30-degree angle. It'll come out to something like this. Notice these are not vectors, these are ropes, right? So to draw the vector, you want to scale the length of the vector should be according to what the force is, what the tension is. So here's my 500-pound force at 60 degrees. Here's my, well, I don't think I have this quite to scale, but you get the idea. Here's my 289-pound force, and this is supposed to be 30 degrees. Okay. Well, that looks like a net force up, doesn't it? That looks like, well, if you put those two forces together, you're going up. Yeah, but we're not going up. So why aren't we going up? Because the weight is pulling down with exactly the opposite direction and exactly the same force as whatever this adds up to. So if you were to draw these two vectors out and say, well, I got 500 at this angle. Let's see, did I do this one? Okay, I found it. So I've done this before. I sketched it out nice and accurate, and I invite you to do the same. And it turns out that this was due north, or straight up, I should say, and it was just about 577-ish pounds, maybe 578, something like that. And so, again, these two forces add up to 577, so if it's not moving, we must have another force pulling it back, which of course is this weight here, and it has to be pulling it back with exactly the same strength. So it turns out that weight must be 577 pounds. Okay, cool. So that's just the basic idea of static equilibrium, which I find is a fascinating idea. You can use this to help you build your beams and stuff with your various on the property projects. But anyway, yeah, so tip to tail is the main idea. Be able to use a protractor is another main idea. Be able to specify your angles in these two different ways, standard position and as a bearing. Be able to work with both, be able to express your angles in both forms. That would be good.